Hi, I am Elmas, a member of the Astra team from the Polytechnic University of Turin. Our shared passion is space colonization, and our first project is truly exciting. We are working on prototyping a pendulum-driven spherical rover. Two opposing motors positioned on the equatorial plane of the sphere provide propulsion for forward and backward motion. A pendulum connected to the motor shaft stabilizes the rover by counteracting the torque generated by the motors. The ability to curve the trajectory is made possible by the inclination of a pendulum, which tilts the rover to right and left, enabling a unique steering capability. Our enthusiasm for space exploration guides every step of this innovative project. The purpose of the simulation is to understand the system's behavior over time in response to various conditions and inputs that influence the system. This involves the observation of variable variations within the model and the evaluation of specific outputs in response to certain inputs. We have then recreated our rover plan model in a simplified manner on Simulink, where we maintain the essential elements for a clear and comprehensive definition of our system's dynamics. This model takes dedicated input torques for forward and steering motion, providing output information on position, velocity, and acceleration thanks to measurements obtained by sensors introduced. These measurements serve as feedback of our system's behavior. As an initial approach to our system, we decouple the dynamics of forward and steering motions. Consequently, we identify two independent control directions: longitudinal, perpendicular to the axis of the shaft, and transverse, along the axis of the shaft. Through a first-order sliding mode controller, we implement position control for the rover's forward motion, setting a predetermined path. SMC is a non-linear control technique aimed at keeping the system on a sliding surface through the manipulation of the control variable. In this case, the control is applied to maintain the desired position of the rover. The SMC dynamically acts to reduce the sliding variable, the error between the current and desired position. The control action is then transformed into a set velocity for the motors, appropriately modeled, including their dynamics, which will influence the effectively applied torque. The output is sent as a command to the rover plan model, in particular to the two joints connected to the spherical shell. A key feature of SMC is its adaptability to variations in system parameters and disturbances, keeping the rover on the desired path. This is particularly useful in complex systems like a spherical rover that may encounter irregular surfaces. For the rover's steering motion, we utilize a pendulum to control the vehicle's steering angle. The control of the pendulum angle is achieved through the implementation of the linear quadratic regulator, LQR. Therefore, its application necessitated, first and foremost, the linearization of the mathematical model describing the steering dynamics, with the assistance of the model linearizer, establishing a reference to follow in terms of the pendulum's inclination angle. The output yields an optimal control matrix used to calculate the control action. This is based on minimizing a quadratic cost function representing the deviation from the desired behavior. The control action is then covered into a set velocity for the motor that controls the pendulum, adequately modeled to include its dynamics, influencing the effectively applied torque. This output is transmitted as a command to the rover plan model, in particular to the joint between the shaft and the pendulum, to reach and maintain the desired pendulum angle. The final step of our approach to the problem involves decoupling of the two dynamics and the simultaneous and parallel execution of the decoupled control of the two main motion directions. This means that we will now provide a trajectory in the XY plane for our rover to execute. It will be decomposed into a desired input in terms of X position for the forward direction control provided by the SMC and a desired input in terms of pendulum inclination for the steering direction control provided by the LQR. Specifically, when the lateral coordinate is different from 0, a certain desired profile in terms of pendulum angle is commanded to LQR in order to track the desired lateral profile. Simultaneously considering a fixed curvature radius of the trajectory for construction reasons, SMC will receive a different desired forward velocity input each time the rover is instructed to turn, enabling it to follow the desired trajectory.